In this video, I will discuss the JEE Advanced PYQ from the topic Thermodynamics. First, I will discuss some basic concepts. When we consider gas moving from state 1 with pressure P1, V1, temperature 1 to state 2, pressure P2, volume V2, and the temperature of the gas is T2. State of the gas can be specified by its pressure, volume, and temperature. So, can we relate the quantities of these two states? Let me consider an ideal gas. Ideal gas will follow this equation of state P1 V1 equal to nR T1. This is at state 1. Similarly, at state 2, PV equal to nRT is valid. So P2 V2 equal to nR T2. For a fixed amount of gas, the number of moles is fixed and R is a universal gas constant. So if I divide these two, I'll get ratio of pressure into the volume ratio, or I can do 2 by 1 final by initial into V2 by V1 equal to T2 by T1. So I'll get this result. Pressure ratio into volume ratio equal to temperature ratio. This for a given amount of gas. Another basic concept is first law of thermodynamics. If we supply heat to a gas, say dq, then the thermal energy of the gas will increase by an amount du, and some part of the heat supply will be used for doing the work, PdV. Let me consider the gas inside a piston, cylinder with piston. The gas is in this enclosed volume. Let the piston be here at the initial state, state 1, and heat is supplied to it. So the volume is expanding and the piston is moving to state 2. So this is state 2. So the total amount of heat added when the gas goes from state 1 to state 2, I can get this from integrating this one from 1 to 2. So that will give me the total heat added delta Q when it goes from state 1 to state 2 is delta U plus integral PdV from state 1 to state 2. So when this piston moves by a small distance, dx, so this is the increase in volume dV. So this dV can be written as A into dx. A is area of the piston, let it be a circular piston, and this move distance is dx. So the increase in volume is volume of this region, which is A into dx. Initially, let the piston be at rest with gas pressure P1 on the left side and atmospheric pressure on the right side. So since the piston is in balance, the force balance equation will give me P1 into A is balanced by the atmospheric pressure P2 into A. So from this, I'll get the initial pressure as the atmospheric pressure. The piston is in balance, so the force on this side is P1 into A. The force on this side is P atmosphere into A. Since the piston is at rest, both the forces are equal, so we'll get P1 equal to P atmosphere. Once the heat is supplied, the pressure will increase. So obviously, as we have extra force from this side. So to get the extra force, one way to get it is you have a spring here attached to a fixed support. So when it comes here, the gas pressure will be P2 and atmospheric pressure is there plus the spring force. Let this distance be x. So at this position, the force balance equation will be P2 into A. Force on this side will be the atmospheric pressure into A. Plus the spring has got compressed by an amount x. So spring will push in this direction by a force K into x. So with this basic understanding, you can solve this JEE advanced question. This is the question. You can read it. An ideal monatomic gas is confined in a horizontal cylinder by a spring loaded piston as shown in the figure. Initially, the gas is at temperature T1, pressure P1 and volume V1, and spring is in its relaxed state. The gas is then heated very slowly to temperature T2, pressure P2 and volume V2. During this process, the piston moves out by a distance x. Ignoring the friction between piston and cylinder, the correct statements are: option A, if V2 equal to 2V1 and T2 equal to 3T1, then the energy stored in the spring is 1/4 P1V1. Option B, if V2 equal to 2V1 and T2 is 3T1, then the change in internal energy is thrice P1V1. Option C, if V2 equal to 3P1 and T2 equal to 4T1, then the work done by the gas is 7/3 P1V1. Option D, if V2 is 3V1 and T2 is 4T1, then heat supplied by the gas to the gas is 17/6 P1V1. You can pause and run this question. It's multiple choice, so you have to check all the options. Option A, volume ratio is 2, volume has increased twice, and temperature ratio is 3. I have to find energy stored in the spring. Energy stored in the spring is half K x square. X is the compression, total compression, which is represented by capital X. So the increase in pressure of the piston that will create a force which is balanced by the spring force, which is K into capital X. This is one equation. Second one, the increase in the volume between the two states. It's V2 minus V1 that will be equal to A into X. Initially the piston is here, say state 1, and state 2 the piston will move here, and this movement is X. This volume is V1 and the volume from here to here is V2. So V2 minus V1 is this volume, the increase in volume, which is this movement X into the area of the piston. So this is the second equation we have. The third equation is pressure ratio P2 by P1 into the volume ratio, which is 2, equal to the temperature ratio, which is 3. This is the form PV equal to nRT. nR will cancel, so pressure ratio to volume ratio is temperature ratio. This comes from the ideal gas equation PV equal to nRT, and this is an ideal gas. So you have three equations. From this side we get half x kx square, which is the spring energy. So from here I'll get P2 equal to 3 by 2 P1. This is equation 3 from 3. So using this thing here, P2 minus P1 will become 3 by 2 minus 1. That's half P1. This is using 1 and 3. P2 is P by 2 P1 minus 1, so half P1 into area. Area I'll use this one, V2 minus V1 by X. And V2 is twice V1. So twice V1 minus V1 is V1. So V1 by A is V1 by X is A. So this will be V1 by X. A is V2 minus V1 by X. V2 minus V1 is V1 by X. That's equal to Kx. So I use 2 also. So using equation 1, 2 and 3. Using 3, I'll write P2 as 3 by 2 P1. And using 2, I'll write A as V2 minus V1 by X. And V2 is twice V1. So V2 minus V1 is V1. So V1 by X equal to Kx. So if I take this X here, I'll get Kx square. And then I divide by 2 on both the sides. So that will give the answer. So X, if it comes on the right side, will become Kx square. And it will become half P1 V1. So I'll divide by 2 on both sides, will become 1/4 P1. Then this is simple manipulation. So I got this half Kx square, which is the spring energy. So option A is true. Option B, volume ratio is same, temperature ratio is same. I have to find the change in internal energy. Option B, pressure ratio change and volume ratio change is same as the one in the option 1, option A. Change in internal energy is same, CV delta T. And temperature ratio is option B is same as option A. Temperature ratio is 3. So T2 minus T1 delta T is T2 minus T1 and this is 3T1. So this becomes 2T1. And we can use the ideal gas equation. P1 V1 equal to NR T1. So NT1 I can write as P1 V1 by R. So delta U will become NT1 will combine. So CV into 2, this 2. So NT1 is P1 V1 by R from this gas equation. And CV is R by gamma minus 1 for a ideal gas. CV is R by gamma minus 1 into 2 P1 V1 by R. So R will cancel. And for a monoatomic gas, gamma is 5 by 3. So 5 by 3 minus 1 is 2 by 3 into 2 into P1 V1. So this will be thrice P1 V1. Simple manipulation. Option B says just 3 times P1 V1. So option B is also true. For option C, volume ratio is 3, temperature ratio is 4, work done by the gas. You find work done by the gas. Option C, work done by the gas is integral PdV from state 1 to state 2. At any intermediate state, this is the initial state of the piston, C1. This is the final state of the piston, 2. Any in-between state, let me call it I. The pressure here, let it be P. So this pressure balanced and the spring will get compressed by an amount. If this movement is xi, this spring will get compressed by xi. So the spring force will be K into xi. So at this intermediate state, the increase in pressure, P minus the initial pressure into A is balanced by the spring force K into xi. So from this I'll get a important result. Pressure as a function of x. So this will be P1 plus K by A xi. A take it here will become K by A and P1 on the right side. So pressure is initial pressure plus the extra pressure which is heating of the gas that's balanced with a spring force by an amount Kxi. So if I use this thing here and dV is A into dx. So work done will be integral P is initial pressure P plus K by A xi into dV is A dxi. So the variable is xi. Xi will vary from initial x equal to 0 to final x, the total displacement x. So the only variable here is xi. So the first term will give me P1A integral dxi from xi equal to 0 to capital X. Origin of xi is here. So xi will vary from 0 to the total displacement which is capital X. So this will give me x plus a and a will cancel. So k xi square by 2 between the limits will become x square by 2. So it's half k x square energy stored in the spring. Okay, and this P1 AX. Okay, so this is written for option A. So same thing I have to write for option C, where the pressure ratio. For option C, temperature ratio, volume ratio, and temperature ratio are changing. Option C, the volume is increased thrice, temperature 4 times. So pressure ratio to volume ratio, which is 3, equal to the temperature ratio, which is 4. So this will become 4 by 3. So same thing as done in the option A with the new volume ratio and temperature ratio. I have to find again half kx square. So P2 minus P1 will become 1/3. Again, using all these three equations to get half kx square. P2 is 4/3, so it will become 1/3 P1. A I'll get from here. A is V2 minus V1 by x. V2 minus V1 is 2V1. Volume has increased 3 times, so V2 is thrice V1. So 3 minus 1 is 2. So 2V1. V2 minus A is V2 minus V1 by x. E I'm elementing from here, which is V2 minus V1 by x. V2 minus V1 is 2V1 by x equal to k into x. So x, if it comes, this will be kx square. And this 2, if it comes down, it becomes half. So I'll leave one. I have 3 P1 V1. So spring energy is half, 1/3 P1 V1. So that I'll use here. 1/3 P1 V1. All the answers are in terms of P1 V1. And this AX I can get from here, which is V2 minus V1. Volume has increased, so it's 2V1. So P1 into 2V1. AX is V2 minus V1. V2 is thrice V1. So this increase in volume is 2 times V1. So 2/3, 2 plus 1/3. So 3 2s are. So I can keep it like this: 2/3 1 P1 V1. So that is 7 by 3. So the work done by the gas is 7/3 P1 V1. Option C says 7/3 P1, so option C is also true. Option D, the volume ratio is same as option C, thrice, and temperature ratio is same as option C, which is 4 times. Heat supplied to the gas. Using first law of thermodynamics, option D, heat supplied to the Q or delta Q, which is equal to delta U plus work done. Work done in option D is same as option C because the increase in volume and temperature ratio are same. So work done is 7/3 P1V1. You have to find this delta U, which is NCV delta T, which is T2 minus T1. So NCV, temperature has increased 4 times in option C and D. Temperature increased 4 times. So this is 4T1, so it's 3T1. And use the gas equation. P1V1 equal to nRT1. So NT1, this NT1. CV is R by gamma minus 1. CV is R by gamma minus 1. 3. NT1 is P1V1 by R. So R will cancel. Gamma minus 1, gamma is 5/3, so it's still 2/3 into 3. So it's 9/2 P1V1. So this is delta U. And work done is 7/3 P1V1. Work done is same as the one in the option C, so it's 7/3 P1V1. So delta Q will be 9/2 P1V1 plus 7/3 P1V1. All the answers are in terms of P1V1. So this is 4 plus half, and this one is 2 plus 1/3. So this is equal to 6 plus 5/6. So it's 41/6 P1V1. Option D is 17/6 P1V1. So option D is false. So A is true, B is true, C is true, D is false. That is the correct answer. So this is what I explained here. Option A, you have to find the energy stored in the spring, which is half kx square. This is the total displacement of the piston moving from state 1 to state 2. Force balance equation of the piston, increase in pressure into the area, that is balanced by the spring force, which is k into x. Increase in volume, is the amount of volume increase due to the movement of the piston by x. So it's A into x. And then volume ratio is 2 in this option. So if we use V2 as 2V1, I'll get V1 equal to A into x. And pressure ratio into volume ratio is temperature ratio. This comes to the ideal gas equation, P equal to nRT. So option A, volume ratio is 2, temperature ratio is 3. From there I get P2 as 3 by 2 P1. So solving these three equations together to get half k x square. So P2 is 3 by 2. So P2 minus P1 is half P1 V1. E is V2 minus V1 by x. V2 minus V1 is V1. So it's V1 by x equal to k into x. So if it takes x on the other side, I'll get kx square. And then to get half k square divided by 2 on both the sides. So half k square will come out to be 1/4 P1 V1. So option E is true. Option B, the volume ratio and temperature ratio are same for option A and B. So increase in energy is NCV delta T. T2 is thrice T1. So T2 minus T1 is twice T1. And NT1 I can eliminate using the ideal gas equation P equal to nRT for state 1. So NT1 I can get from here. And CV is R by gamma minus 1. So putting that thing here, and gamma for monoatomic gas is 5/3. Simplifying, you get answer as 3 thrice P1 V1. Gamma is 4/2 for monoatomic gas. So option B is also true. Option C, the temperature volume ratio is 3, volume has increased 3 times, and temperature has increased 4 times. So pressure ratio into volume ratio, which is 3, equal to the temperature ratio 4. So from this I'll get the increased pressure P2 as 4/3 of the initial pressure 1. So from the equation 1, increase in pressure, which is P2 minus P1, that's 1/3 P1 into A is the spring force. And A is increase in volume V2 minus V1, which is 2V1 by X is A. Go to case from this, I'll get half k square as 1/3 V1 V1. Work done by the gas is integral PdV, and pressure in any intermediate state is the initial pressure plus the pressure balanced by the spring force, which is kx1 by A into dV is A into dx. So this can be integrated term by term. Only variable is xi. P1 is constant, E is constant. So P only will come out, and equal dxi is A into x. So that is change in the volume V2 minus V1, which is 2V1 plus half kx square, which is 1/3 V1 V1. So 2 plus 1/3 is 7/3. So option C is true. Final option, option D, we have to find the heat supply to the gas when the volume has increased thrice. Work done is same as the option C, because for option C and D, the volume ratio and temperature ratio are same. So NCV delta T, T2 is 4 times T1. So temperature difference is 3 times initial temperature. CV is R by gamma minus 1. And using the ideal gas equation, PV equal to nRT. nRT1 can be written as P1 V1. And gamma minus 1 is 5/3 minus 1 is 2/3. So simplifying, we get 41/6 P1 V1. So option D is not true.